Welcome back to our series on multivariable calculus. In this episode, we're going to look at partial differentiation. We're actually going to learn about it as a result of an example. We're going to use the example and extend what we learned there to form the definition of a partial derivative. The example I'm going to use is one we're familiar with. I'm going to redraw the paraboloid f of xy is equal to x squared plus y squared. And you recall from the last episode that basically forms a parabola-like shape that's three-dimensional that wraps around the z-axis, this being the y, z, and x-axis. Now what I want to do actually is carve into this in a very similar way that we did to determine what this thing's overall shape was, except this time I'm just going to use a single plane, and it's not going to be axial. It's actually going to be a plane perpendicular to the y-axis at a specific location, y equals 2. And what I want to do now is generate a plane that carves up and through this shape. It's basically going to carve out a little piece of it. It's going to look like this. And what I want to do is examine that by turning the graph and examining what the intersection is of this plane together with that little carved slice of the paraboloid. When we turn it, here's what it's going to look like. Again, we're looking straight down the y-axis, so the x-axis will feature the horizontal, and of course the z-axis will feature the vertical. And it won't intersect it right there at the bottom. Instead, it's going to skip all the way up to where the intersection first begins. And of course, if y equals 2, we can see where that's going to be. If I just substitute y equals 2 into the function, then the new function I'm graphing is going to be just f of x, because y is already chosen, and it's going to be x squared plus 4. That makes a parabola that begins at 4 on the z-axis and opens upward. So this, in essence, is going to be the graph of the cross-section once I carve it with this 2. Now this just becomes a single variable function, which means if I wanted the slope of this parabola at any point, I just take the derivative of the z function, or the derivative of f. That is df dx. And of course, that's pretty easy. That's just going to be 2x. Well, think about what we just did. We took the derivative of f while holding the y value constant. Now, you might think there's something unique about this plane y equals 2, but there really isn't. I could move this plane back and forth to any value. If I were to shift it instead of y equals 2, it would be y equals k. Well, look what that would do to the original function. If I substituted k in there, it would still make it a variable of a function of one variable. It would be f of x equals x squared plus k squared. And now the first derivative of that, df dx, would still be equal to 2x. In other words, it doesn't really matter how I carve this with any plane that's perpendicular to the y-axis. At any location that intersects, it's always going to produce a new single variable function whose derivative is always going to be 2x. And what we've basically revealed is the idea of a partial derivative. For this 3D function, if I were to hold y constant and just differentiate it in the x direction, I'm only going to get one answer. Now, that means this is a special derivative. This is a derivative of f while y is being held constant. And we're going to give that a new name. We're going to call it a partial derivative. So here's kind of the way the notation works. It's df dx under the condition that y is equal to a constant. So we're going to change the notation for it. I'm going to use a cursive d instead of a regular solid d that we complete. So it's going to be df dx. And we even have a separate symbol for that. We write this so much that continuing to write it as a ratio can be tedious. So we just call it f sub x. So use the same symbol for the function, but then add a small subscript x to it. And that references that this is the derivative with respect to x holding y constant. Well, it turns out this is the definition then of a partial derivative. We can take any multivariable function and take its partial derivative, treating all of the other variables as constant. In this case, there were only 2 variables, but this works for 3 variable, 4 variable, and 5 variable functions. In essence, we can take the partial derivative of any function holding its remaining values constant, and what it gives me is the slope in the plane perpendicular to those axes that we're holding constant. Okay, well, let's take a look at the other partial derivative of this function. If I wanted to evaluate now fy, well, that would also be equal to 2y because we would be holding the x constant, and that means the x as a constant differentiates out. Well, this looks great in terms of this unique function, but let's make up another function and look at what its partials would be. Maybe a more complex function whose cross sections aren't so easy. It's one of the reasons I chose this one to start with, because it had cross sections that are so easy. Let's take a look at another function. Suppose our f of xy is more complex and mixes in the x's and y's. So it's 3xy squared plus 2x squared y. Well, we can still take partial derivatives of this. It would be more complex because this function isn't going to have a shape that has a consistent cross-section every time I slice it with a vertical plane. But nonetheless, the same principles apply. fx, that is the derivative of this with respect to x, holding all the y values as constant would be, well, again, the 3 and the y squared are constant, so they become the coefficient of x. The power real simply says it's the coefficient, so it's 3y squared plus, and again, I'm just taking the derivative with respect to x. I'm holding the y constant, so 2y is the coefficient. I bring down the 2, reduce the power, so it's 4yx. This would be the partial with respect to x, and notice the difference between that and this function. This one had a partial with respect to x that was only a function of x. This one has a partial with respect to x that is also a function of y. What does that tell you? Well, it tells you as this plane moves back and forth in this function, the actual shape of the cross-section changes. It's a function of y. That doesn't negate the ability of the partial derivative to still give me the slope. It still gives me the slope in the plane containing y. It's just now that slope is dependent upon which plane I choose. Correspondingly, the other partial derivative, fy, is going to be equal to, again, holding the 3x constant, this will be 6xy, and holding the 2x squared constant, that will be the coefficient, 2x squared. So there's the partial derivative in x and y. Well, let's take a look at a great application of the partial derivative so that we can see what value it has in producing as close as we're going to get to the slope of a multiple function, of multiple variable function. Okay, let's take a look at a surface, and just like we did with derivatives in single variable calculus where we found a tangent line, so if we had an xy function that was graphed, we knew that if we found the derivative at a point, so this point would be a, b, then we could find the derivative, that is, we could find f prime of x, and then plug in a, and that would give me the slope of a tangent line. In other words, f prime of a would be the slope of this line right here. And then knowing a point on the line, AB, together with this slope, we could actually find the equation for that tangent line. Well, a surface doesn't really have a tangent line, because if I mark a point on it, the artifact that will be perpendicular to that point isn't a line, it's a plane. So how do we go about finding the tangent plane to a surface, which is analogous to finding the tangent line to a function in 2 dimensions? Well, let me show you how it works. Suppose I have a function f of xy, and it sort of looks like this. That is, within the plane, there's a small section of it, and it curves off into the distance. So this is a curved surface, and I'm going to select one point on that surface. I'll call it AB. Again, AB, and then it'll have that third coordinate, that C value, which will give it the height, but it's really AB that defines where it is. Again, then it'll also have the function value. So I'll put in C, but that's just the Z value that corresponds to the A and B. Well, because this surface is curved, I want a plane that's actually tangent to that point. So there'll be a plane there that exactly contains that point and is and basically brushes by the surface, so it only contains that point. That is, it's truly tangent to the surface. Well, how do we go about finding that plane? We know enough about planes now to know how we're going to actually locate a plane in space. We need 2 things. We need the normal vector and a point that lies on the plane. We already have a point that lies on the plane, So I need the normal vector, something that points perpendicular to that plane that can help me isolate it as different from any other plane that contains point ABC. Well, just as we did when we were finding the equations of planes, one easy way to do that is to find two vectors that lie in the plane and then take their cross product. And that will give me a normal. Any old normal will do. It doesn't have to have any magnitude. It just has to point in a direction. Well, the two vectors that are easiest to find are actually going to be informed by this idea of a partial derivative. Let me tell you what those two vectors are. So once again, I'm looking for two vectors, vector u and vector v, that both lie in this plane. Vector u is going to be along the x-axis, and to guarantee that, all I have to do is give it a coordinate of 1 in the x, so it points along the x, and 0 in the y. That guarantees that it points exclusively along the x-axis. And then here's the trick. Its z-coordinate is going to be the partial derivative with respect to x evaluated at a and b. That will, in essence, give me the slope. So the y-coordinate of this vector will be the slope that it has at that point, and it will point in a direction along the x-axis. So this provides me with one vector, and it's very convenient. That's one of the values of the partial derivative, is it'll tell me the direction it's pointing in the x direction. Of course, I think now you can see how we'll form vector v. Vector v I want to be along the y-axis, so I give it coordinates 0, 1, and its z-coordinate will be the partial with respect to y evaluated at a and b. This will be the slope along the y direction. And of course, this vector definitely points down the y-axis because I've given it the first two coordinates, 0 and 1. Now, you may well wonder, how can I just make these vectors up? Well, keep in mind, I just need any two vectors that lie in that plane. I'm not looking for any particular ones, so it makes sense to find the easiest ones I can locate, and these are them. Now, the next step is pretty messy. I want to take the cross product of these so I can find the normal to the plane. I'm going to skip through the messy work. You can do it on your own if you like. This is what it turns out to be. We get fx for its x-coordinate evaluated at a and b. We get fy for its y-coordinate evaluated at a and b. And we get -1 for its z-coordinate. That's the normal, and we have a point a, b, and c. So now we can simply write the equation for the plane using the tools we already have. I can say that it's going to be ax plus by plus cz is equal to d, where a, b, and c are actually provided by these coordinates right here. And the point ABC can then be substituted in for x, y, and z. I made an unfortunate choice here because I chose the point at the location to be ABC. And of course, we know the equation of the plane, the a, b, and c, are actually the direction numbers provided by the normal vector. But you'll be able to figure that out. In essence, that's how you find a tangent plane to a point on a 3D surface. Okay, so we'll see more applications of this partial derivative as we move on, and we'll be using partial derivatives throughout. They are the bread and butter of multivariable functions.